let's examine the derivative just a little bit more. The derivative of a function y equals f of x is the slope of its tangent line. So if I were to take an x value, I can come up to my function. I can imagine the slope of the curve, the slope of its tangent line at that point. So the slope of that line, that would be the value of the first derivative at that particular point. And there's nothing special about that point. I could do that at all of the points. And so what I'm imagining now is that for every point here, where I can come up and draw a tangent line, I'm plugging in x, I'm getting out the slope of that line, right? And again, I could just continue doing that for all of the x values here, right? And some of my slopes are positive and some of them are negative and some might even be 0. But for every x, I can imagine the derivative as a machine that gives me back the slope of this curve. And that leads me to the realization that the derivative itself is a function. The function takes an x and turns it into a y. The derivative takes that x and turns it into a slope. The derivative is a function. So we can reevaluate, rethink our definition of derivative, thinking of it as a function. The derivative of y equals f of x, denoted by f prime of x, is f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h, provided the limit exists. Well, this is not really a change for us. The last time I wrote down the definition of derivative, where all of these x's were a. And we were thinking of a as a particular value, right? A particular x value. Well, now what I'm realizing is any of these values would work. So I can just call it x and then get a actual function for my derivative. I plug in an x and I get out a slope. So let's do an example. Find the derivative of f of x equals 2x plus 3. All right, well, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. All right, replace the x with an x plus h minus f of x. All right, I want to emphasize something about what I've written here for a couple reasons. When I subtract f of x, I need these parentheses. I'm subtracting all of f of x. And this is a very common mistake in a first calculus class, where students will omit that set of parentheses. And if you omit that set of parentheses, instead of subtracting that plus 3, you're accidentally adding it. When we do that, we'll never be able to cancel this h off the bottom, and we won't be able to calculate the first derivative. So be very, very careful with that grouping symbol. It's important. All right, I have to distribute 2x plus 2h. I have that plus 3, minus 2x, and minus 3, all over h. All right, the plus 3 and the minus 3 cancel. The 2x minus 2x cancel, and I have the limit as h approaches 0 of 2h over h. Those h's cancel, and I just get the limit as h approaches 0 of the constant 2 is 2. For every value of x, the derivative of this function is the number 2, and that makes me feel good because this is a line. The slope of this line everywhere is 2, and that's what this is telling me. The slope of that line for all values of x is 2. All right, well, linear functions are super boring. Their derivatives are always their slope. So let's do another example that's not quite so boring. Find the derivative of y equals x over x plus 1. Y prime is the limit as h approaches 0 of, all right, x plus h goes in for x in every appearance of x. Fraction bar wasn't in a good spot. All right, so I have x plus h all over x plus h plus 1 minus f of x, x over x plus 1 all over h. I have a compound fraction. We could actually find a common denominator on top and then think about multiplying by the reciprocal of h. I always like to do a little trick that works with compound fractions where I multiply the top and the bottom of the big fraction by the least common denominator of all the little fractions. It's always okay to do the same thing to the top and bottom of a fraction. All right, so on the bottom, I'm not going to multiply anything out. And like I said in one of the previous videos, I never do, because what I really want is to be able to cancel off that h. So I'd want it factored out anyway. All right, so on the top I distribute, and I get that x plus h. This part cancels, and I'm left with that x plus 1 minus x times the x plus 1's cancel, and I'm left with the x plus h plus 1. I need to simplify the top so that I hope I can cancel that h off the bottom. So in the middle of this, I just need to do some more algebra. All right, let's see. I have an x squared plus x plus hx plus h minus x squared minus hx minus x. So I have some like terms on the top I can cancel. The x squareds go away. The x's go away. And even this hx goes away. And the only thing that's left standing on the top is that h. Well, that's a good thing, because that's the one I'm going to get to cancel. So I'm going to write that on the next board, and we'll finish off finding this derivative. All right, the h's cancel. And now I can take the limit as h approaches 0 because I'm not dividing by 0 on the bottom anymore. H is going to 0, which would turn this into an x plus 1 times an x plus 1 is x plus 1 squared. And there I have it. There is my first derivative, f prime of x. All right, so I started with a function. Let me see, I called that y, so I need to write that down as y prime. My function y was x over x plus 1. If you plug x's into this, you get y values. If you plug x's into this, you get slopes, the slopes of tangent lines. All right, we'll do another example here in a minute, but that's it for now.